Let's use the BLAST tool to align a relatively short sequence against a genome. If the sequence comes from a gene annotation or a marker, then the easiest way to BLAST it is to open its Details dialog, click on the appropriate sequence tab, then click the BLAST button. The Run BLAST dialog will open up, pre-configured with the sequence as the query. But you can also run BLAST manually by clicking this button on the main toolbar, pasting your query sequence into the query box, and then selecting the appropriate BLAST program type. In this case, we want to align a protein sequence against DNA, so let's select tBLAST-N. Now let's select the target map sets for alignment. You can mix and match entire genomes or individual chromosomes, and the status bar at the bottom will keep a running tally of your selections. The total size of the selected genomes is displayed here and may be limited, depending on Persephone's configuration settings. If you exceed this limit, the length counter will turn red, and you will not be able to run BLAST until you deselect some sequences. You can mouse over the map set labels on the status bar to inspect their sizes, and click the X button to remove them from your selection. Finally, we should select the appropriate BLAST parameters. Persephone provides 3 convenient presets: Fast, Normal, and Primer, which is only applicable to short DNA queries, and an option to supply a custom parameter set. Let's select the Fast preset for now and click this button to run BLAST. The resulting alignments are summarized in the table at the top of this BLAST results dialog, and the tabs in the bottom half provide additional information. Every line in this table represents a high-scoring pair, or HSP. That is, a fragment of the query sequence that matched the subject genome. By default, these are sorted in the same order as they appear in the BLAST output file, but you can sort them by another column if you wish, such as %identity. You can also click this button to export all of the HSPs using Persephone's standard export interface. The Map tab at the bottom displays the distribution of HSPs on the subject genome. In this case, BLAST found some close matches on the first chromosome of beet, as well as some loose matches on multiple chromosomes of corn. The currently selected HSP is highlighted and indicated by this triangle icon. You can click any other hits in the Map tab to quickly select them in the main table, and vice versa. The BLAST alignment for the current hit is always displayed in text form at the bottom of the dialog, but the Alignment tab presents a more convenient graphical view. Here, the query sequence is shown at the top, and individual HSPs are chained together into a more coherent model of the entire match. The subject genome is shown at the bottom and is always shown in the forward orientation, with the 5' end on the left. In this case, because the hits happen to align on the reverse strand, the entire query sequence is facing to the left. The currently selected HSP is drawn in a bold color and indicated with these triangle icons. This ribbon connects the hit's location on the query to the genome. Blank spots in the ribbon represent mismatches or insertions. You can roll the mouse wheel to zoom in around the mouse cursor or zoom out to see more hits at a glance. You can also click an HSP to select it in the main table. For now, let's select a hit on the first chromosome of beet and click this button to display the BLAST alignment on the map in a new track. It looks like BLAST found an orthologous gene annotation, which is not surprising considering that the original query came from a different assembly of beet. However, BLAST mistakenly chose to concatenate these 3 exons into a single HSP. To fix this problem, let's click the BLAST hit to return to the BLAST results dialog. Click this button to return to the previous screen and override the BLAST arguments. You can click this button to adjust some of the most common parameters visually, and you can click anywhere inside the text box to recall a list of most recently used parameters. For now, however, let's manually enter in the arguments to increase the gap penalty. Now, when we rerun BLAST, it will correctly identify all of the individual exons. We can also run BLAST to align DNA sequences against a genome. For example, let's use BLAST-N to validate some primers. This time, the input contains two query sequences, one for the forward primer and the other one for the reverse. These primers were designed for Arabidopsis, so we will select it as the subject. By the way, you can quickly deselect all of the genomes by clicking the tri-state checkbox at the top. Now let's set the program type to BLAST-N and run BLAST, which fails to find any hits. This is because we use the FAST preset with the word size of 28 nucleotides, but our queries are only 20 nucleotides long. The primer preset happens to specify the word size of 20, so if we select it and rerun BLAST, we will see some hits. Because we used more than one query sequence, we can now see the query selector in the upper left corner of the dialog. Both of our query sequences are listed here, along with the number of HSPs produced for each query, and we can use the checkboxes to show or hide those HSPs in the main table. It looks like both of the primers achieved a good alignment with 100% identity. However, once we zoom out, we can see that each primer pair aligns to the genome in multiple places. Once we display these hits on the map, it's easy to see that several pairs of primers are bracketing gene annotations between them, and so these primers would not be good candidates for an assay, as their PCR products would not be unique. As you've probably noticed, Persephone will display individual nucleotides in the alignment view, provided that the query is sufficiently short, and it will also display any overhanging nucleotides that were not matched by BLAST. For example, if we go back and add an extra C to the query, then it will be shown in the alignment view, even though BLAST omits the extra C from its own alignment block.